Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. Blue jeans are blue because of a few grams of indigo dye, which has been used by many human civilizations throughout history. In fact, the oldest known fabric dyed with indigo is a staggering 6,000 years old and is from Peru. Back then, we got the dye from a variety of plants, but demand is quite a bit higher these days, and the amount of indigo we extract from natural sources can't keep up. Luckily, chemists in the 19th century came up with a number of ways to make indigo dye in the lab. The main method used today involves a compound called aniline as a starting point, which can be produced from nitrobenzene, which we met back in episode 37. Though it's useful for that blue jean color, the synthesis of indigo also involves formaldehyde and hydrogen cyanide. Not exactly the nicest compounds to work with. So a challenge for chemists today is coming up with a synthesis for indigo that avoids these chemicals. Aniline can sometimes be too reactive, and its precursor, nitrobenzene, is sometimes not reactive enough when it comes to electrophilic aromatic substitution reactions, or EAS for short. Luckily, we've got some chemical tricks up our sleeves to work around this. In episode 37, we met a specific kind of EAS called Friedel-Crafts reactions, and we used them to add alkyl and acyl groups onto a benzene ring. Both reactions use an aluminum halide as a catalyst, commonly aluminum chloride. In Friedel-Crafts alkylation, an aromatic ring is reacted with an alkyl halide. And in Friedel-Crafts acylation, we use an acyl halide. Like we've said before, these reactions are an important part of an organic chemist's toolbox. We can make carbon-carbon bonds with aromatic rings, but like many reactions, there are times when they just don't work like we want them to. Specifically, there are three key problems we can run into. Problem one is when we have a deactivated ring. Remember from episode 38, electron withdrawing groups can pull electron density away from our benzene ring, making it less reactive in EAS reactions than plain benzene. So what happens when we try and carry out a Friedel-Crafts reaction with a deactivated ring? Not a lot. The benzene ring is too electron deficient to react, and there's usually no reaction with these electrophiles. In some cases, Friedel-Crafts acylation will work where alkylation doesn't, because the acylium ion is a slightly better electrophile. But with a strongly deactivating substituent like nitrobenzene, both reactions are tricky. The way to get around this problem is to counter the nitro group's deactivating effect by having a strongly activating substituent on the ring, like an electron donating group, which pushes electrons into the ring, making it more susceptible to reaction. Problem two is overalkylation. On the flip side to our alkylation reactions not working at all, they can also work almost too well. Because the alkyl groups are electron donating, the alkyl benzene we generate is more reactive than the original benzene. So we could accidentally cause a domino effect of adding more and more alkyl groups to the ring. For example, let's say we want to make ethylbenzene from benzene. We can try reacting ethyl chloride in a Friedel-Crafts alkylation. And at first, everything might go exactly as expected with our EAS reaction and we produce ethylbenzene. But then the reactions could go right off the rails. And before we know it, another ethyl group could add to the ring. In fact, we might end up with a whole mix of overalkylated products. Luckily for us, the solution to overalkylation is simple. Use our other Friedel-Crafts reaction. We don't have the same issue with Friedel-Crafts acylation because the acyl group is electron withdrawing, which offers us a less chaotic route to the ethylbenzene we wanted to make. Instead of carrying out a Friedel-Crafts alkylation with ethyl chloride, we can try a Friedel-Crafts acylation with ethanoyl chloride. After adding an acyl group to our benzene ring, we can reduce the carbonyl group and get ethylbenzene. We're not reducing the carbonyl group down to an alcohol like we've seen in previous episodes. We're completely removing the group. And we'll look at two possible reagents for this reaction. The first option is hydrazine, heated up to 200 degrees Celsius and carried out under strongly basic aqueous conditions. This is known as a Wolff-Kishner reduction. Remember that aldehydes and ketones react easily with amines to form imines. This reaction is similar. Our ketone reacts with the hydrazine first, forming a compound kind of like an imine with another nitrogen attached, called a hydrazone. Then a base-catalyzed isomerization helps make a nitrogen-nitrogen double bond, and a final deprotonation makes a triple bond. This produces nitrogen gas and leaves us with a carbanion. And protonating this carbanion gives us the alkyl benzene product we're looking for. We're done. We have to be very careful when we form a gas in the lab because it can build up pressure and potentially explode. But this can be helpful too. A reaction that rapidly forms nitrogen gas is what inflates airbags in a vehicle crash and can save your life. Another option to completely remove a carbonyl group is a Clemmensen reduction, which uses zinc amalgam, a mixture of zinc and mercury, to reduce the carbonyl group to an alkane. This mechanism is a little more complicated and involves radicals, so we won't get into it here. Getting back to our Friedel-Crafts reactions, the third and final problem we can run into is the carbocation rearrangements we saw in episode 37. The major products we get from our Friedel-Crafts alkylations usually involve the most stable carbocation. For example, the reaction of 1-chlorobutane with benzene gives mostly the rearranged product. In our mechanism, we form an unstable primary carbocation, and if the compound can rearrange to form a carbocation that's more stable, it'll go right ahead and do that. Again, this is a problem we can solve by leaning on the other Friedel-Crafts reaction in our toolbox. Acylation is usually a more convenient way to add unbranched alkyl groups to a benzene ring because the acylium ions they form are more stable and they can't undergo rearrangement. After we add an unbranched alkyl group with Friedel-Crafts acylation, we can just reduce the carbonyl group to remove it and leave us with the alkyl group we wanted. Besides using reductions to solve two of the three main problems with these EAS reactions, we can also use reductions to change the directing effects of substituents we already have attached to the benzene ring. Back at the start, we mentioned that aniline, one of the reagents used to make synthetic indigo, is formed from nitrobenzene. The nitro group is a metadirector, but the amino group, which just has 2 hydrogens instead of 2 oxygens, is an orthoparadirector. So say we want to use electrophilic aromatic substitution to make this ring, with an amino group and a bromine at the meta position. Like we just mentioned, the amino group is an orthoparadirector, and the bromo group is an orthoparadirector too. So how do we get the meta pattern? Well, we can start by adding the meta-directing nitro group and then carry out the bromination reaction, adding a bromine to the meta position like we want. And then we can reduce the nitro group to get the amino group on our benzene ring. Kind of tricky, but we used reduction to get the directing effects we wanted. So far in this series, we've mostly considered EAS reactions with a single substituent on a benzene ring. But we'll come across lots of cases where our benzene ring has multiple substituents, which can make it harder to work out where substitution will happen. In these cases, we have to consider whether the groups already attached to our benzene ring are ortho, para, or meta-directing, as well as their relative strengths. If we have groups with effects that reinforce each other, that can make these logic puzzles easier. Take this example, where we have a benzene ring with a nitro group and a hydroxyl group attached on opposite sides of the ring. The nitro group directs to the spot meta to itself, while the hydroxyl group directs to its ortho or para position. Based on these effects, if we try to add a chlorine atom, there's only one place it can end up: in the meta position to the nitro group and the ortho position to the hydroxyl group. Nice and straightforward. Now, if we have two groups with contrasting effects, the stronger activating group gets priority. For instance, let's look at the nitration of 4-bromophenol. Both groups here are orthoparadirectors, but the hydroxyl group is activating while the bromo group is deactivating. So the hydroxyl group is the strongest and only activating group, and it takes priority. If we try to add a nitro group, the reaction favors position ortho to the OH, and this is our major product. Now, depending on the difference in electron donating ability, these competing directing effect reactions can produce mixtures of products. But now we know the best way to predict the major one. The reactions we have in our toolkit so far allow us to easily add halogen atoms to a plain old benzene ring. A benzene ring with an alkyl group contains a benzylic carbon, the one attached to the benzene ring. And you know what? We can halogenate that easily too. These reactions take advantage of the stability of the benzyl radical. Remember, a radical is a molecule with an unpaired electron, and usually they're very reactive and unstable. However, in the benzyl radical, the neighboring aromatic ring helps stabilize the radical through resonance. So we can carry out free radical substitution reactions at the benzylic carbon. Benzylic halogenation allows us to replace a hydrogen atom on a benzylic carbon with a chlorine or bromine atom. For chlorination, we simply heat our reagent, in this case toluene, with chlorine or expose it to UV light. If we use an excess of chlorine, we can continue to replace the hydrogens on the benzylic carbon with chlorine atoms. We can do the same thing with bromine to add bromine atoms to the benzylic carbon too. And this time, we'll use N-bromosuccinimide, or NBS, as our reagent. Formation of a benzylic radical makes the reaction possible. As we know, bromine is a good leaving group, and having a good leaving group on the benzylic carbon lets us add all sorts of fun groups onto the alkyl chain, which would be difficult to add directly to the benzylic carbon. The usefulness of benzylic reactions doesn't stop there. Benzylic oxidations are a handy way of turning a benzene with an alkyl side chain into benzoic acid. To do this, we can use chromic acid or hot alkaline potassium permanganate as an oxidizing agent. This reaction works regardless of the length of the side chain, but you need to have at least one benzylic hydrogen. Because oxidation begins at the benzylic carbon, during the reaction, the further carbons on the chain are lopped off, giving us benzoic acid every time. These reactions are pretty useful because we can't attach a carboxylic acid group directly to a benzene ring through Friedel-Crafts acylation, so this gives a fairly simple route. Not to mention, benzoic acid has uses as a food preservative and as a precursor to various other products. So whether you're wearing jeans or drinking a can of soda, EAS reactions are all around us. In this episode, we identified 3 limitations of Friedel-Crafts reactions and how we can work around them, saw where substitution happens when we have multiple directing groups on a benzene ring, and introduced benzylic reactions. In the next episode, we'll be heading to the lab to apply these reactions to some synthesis problems, and we'll add additional purification methods to our toolkit. Until then, thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.